X6 Newton's laws of motion. Explain the following figure representing two forces applied to a particle in equilibrium. Two forces are applied and the particle is in equilibrium. In that case, net force is 0 and net torque is also 0. In some case, the force two-body system, a force is applied in this direction, another force is applied in the opposite direction. However, in this case, even though the net force cancels, net torque is not 0, so the system rotates. But this is a single particle, so you don't have to worry about the torque. So in this case, net force cancels exactly. Inertial frame of reference. If you claim this one represents the force, force is well defined only if we describe a system in an inertial frame of reference. In a non-inertial frame of reference, it changes. So, because two forces cancel, F1 is additive inverse of F2. Sure, F1 plus something equals 0. If you have additive identity, as a result, after the sum, this element is called additive inverse. Okay? So F2 is the additive inverse of F1, vice versa. Two forces are linearly dependent. We have only a single direction, and basis vector, number of basis vector is the number of mathematical dimensions. And in here, we have only a single direction, either this or that. And this one evidently shows that 1 times F1 plus 1 times F2 equals to 0. The two forces are linearly independent only if C1 F1, C2 F2 equals 0 if and only if both of them are 0. We have shown that these coefficients are non-zero. At least one is non-zero, then they are not linearly independent. They are linearly dependent. So the only, for example, if I have F1 equals 0, only if C1 equals 0. Yes, F1 is a linearly independent, only a single one. So number of linearly independent available vector is called the mathematical dimension of the vector space. And in this case, we have only a single dimension. That's the reason why this system is completely expressed in terms of a one-dimensional Cartesian coordinate system. The single number line is enough to describe the system. Unit basis vector is either along this direction or that direction. The unit vector out of a vector A, the unit vector, hat vector is obtained by dividing this vector by its own magnitude. And these are magnitudes of F1 and magnitude of F2. F net equals 0. Acceleration is 0. F net sum, algebraic sum of all applied forces is called F net equals m double time derivative of position vector, that is mass times acceleration. The position of a particle is given like that. Here R and omega are constants. Okay, that means it is making a uniform circular motion. Theta equals omega t, and omega is a constant. We can see this cosine theta, sine theta. Okay, so this is a point. This vector represents a circle of unit radius. And then after that, we multiply the constant radius. So it becomes a radius r, and radius is fixed, and angular velocity is fixed. So it is called uniform circular motion. We can take the make use of chain rule to find that we have done that previously. This is just to put it as a theta, and we take the d theta, d cosine theta, and then d theta over dt. So this one is minus sine, and this one is omega. So minus sine omega t. What happens to this? This becomes cosine, and this becomes omega. So omega cosine omega t. If I consider this time derivative of position, that is a velocity, is r times omega, and unit tangent vector. And I can translate this one. This is making a right angle with respect to the original unit radial vector. Note that x dot is perpendicular to x. This is x, and it is perpendicular to. Therefore, ER and E theta, they are perpendicular. So cosine 0, no, cosine perpendicular, half of pi equals 0. The speed of the particle, so take the scalar product with itself, r omega squared, and this is a unit vector. So sine squared plus cosine squared, 1. We take the square root of it because r and omega are positive constant. The answer is r omega. So speed of the particle is r omega for the uniform circular motion. What happens to the acceleration? Previously, in lecture 5, we have considered the acceleration for the most general case in two-dimensional plane. However, we have radius r fixed. It is a very simple problem. In that case, r, e, r hat, we take the derivative, no change, so e, r dot, and then we take another derivative, then it is nothing but er double dot. And er dot, we know that it is a theta dot, e theta, and then this one, theta dot is omega in this problem, so equals r omega e theta dot, and these are constant. Therefore, the second order derivative is r omega e theta dot. And we know this is a minus theta dot er. And this theta dot is omega in this problem. Therefore, we have a minus r omega squared er. And r times er is x vector itself. Therefore, we arrive at this one. If I move this guy to the left-hand side, we will find this acceleration plus omega squared, x equals a zero vector. Actually, this one is a two-dimensional harmonic oscillator. We already know the answer because we began with the answer. This answer satisfies this kind of vector equation. Each Cartesian component satisfies the same equation. Okay, this is a simple harmonic oscillator. So uniform circular motions of two Cartesian components represent the simple harmonic oscillator of the same angular frequency. Because I know what the acceleration is, I can compute the net force applied to this particle. That is based on the Newton's second law, mx double dot. So what I have to do is just multiply the mass in here, minus mr omega squared unit radial vector, and minus er represent the center particle at point P. So er minus er is toward the center, So this kind of force that makes a particle under uniform circular motion is always toward the center, and magnitude is mr omega squared. It is called centripetal force. It is not centrifugal force. Centrifugal force is something like it is going out. That is when we describe this system in a non-inertial reference frame. For example, you are writing this something that is making uniform circular motion. You feel some force outside. That is called centrifugal force. That is not a force. That is just inertia. Instead, that's the reason why you are in a non-inertial reference frame. When we describe a uniform circular motion outside in an inertial reference frame, you can always find that the force is toward the center, and that force is genuine force called centripetal force. Magnitude of the centripetal force is mr omega squared. We know the speed is r omega, so I can make use of this identity to replace it, mv squared over r. X is a position of a freely falling object. Freely falling object, F net is this, and under constant gravitational field, we have exact cancellation of these two masses, and actually this is called inertial mass, and this is called the gravitational mass. Einstein's general theory of relativity states that these two are the same, so they cancel. Finally, our equation of motion is a trivial equation, where g is a constant vector toward the center of the Earth, approximately. We can still integrate this equation once. This is constant, integrated over time from 0 to t, the closed time interval. Then you will find the left-hand side, the difference of velocity. This is acceleration. After integration, after explicit integration over a finite interval, you will find you replace this one with x dot and substitute upper limit and lower limit and difference. That is the definition of a definite integral. And then you shift this one to the right hand side to find out that the velocity at arbitrary time is initial velocity plus the definite integral of this acceleration. And this integral is a trivial, and we know that this is a t. So gt. We can still make another integration that we apply the definite integral on the right hand side and left hand side too. And in here, this definite integral x dot t prime dt prime 0 to t. This one is displacement. Get rid of this dot x, substitute the upper bound, upper limit, substitute lower limit, subtract. This difference is the definite integral from 0 to t. Therefore, we end up with this expression. In here, this one is already, this x dot t is known, so I have substituted this right hand side in here. As we have done in previous class, we know all of the integrals are evaluated like that. So as a result, in general, in any case, x of t, initial position, definite integral of a velocity, and this definite integral of the velocity can be expressed again recursively using this formula. That is initial value of the velocity plus definite integral of one more derivative, that is acceleration. So it is the most general form of the solution in an integral form. You must know very well about the definite integral and then substitute prime prime t and whatever, any constant. So this one is f of t. You learned it a lot of time in high school. So this is the same. Just if you integrate with the same variable and take the derivative with respect to the same variable, then the answer is the integrand itself. If you do this job twice, there are double integrals in here. If you do this job twice, this guy will be gone, this y will be gone, and then the only thing survives, that is acceleration. That is acceleration, but the problem says the acceleration is the gravitational acceleration because we are considering a freely falling object. Next, we consider the two-body system. Center of mass is defined by the weighted average of two position vectors using the weighting factor coming from the relative importance of mass of each particle. If they are identical particles, then it becomes just a center midpoint of the two. Okay, but if they are different, then the center mass will be closer to a heavier particle. We define the linear momentum of each particle by multiplying the velocity by the mass. So mass, velocity. Describe the motion of the two-body system. Because the two-body system is isolated, we do not consider any other forces except for their own interactions. Isolated, so the net external force equals 0. So F net of 1 and F net of 2 is called F net of this two-body system. It is 0. According to Newton's second law, each particle, this is m1 at x1, m2 at x2, they communicate with each other, and we say the force F21 is the force applied to particle 1 by 2. In reverse, F12 represents the force applied to particle 2 by particle 1. That must be the time derivative of linear momentum, and that is, by definition, mass times acceleration of the first particle, and mass times acceleration of the second particle. Newton's third law of action and reaction states that any two objects interacting with each other give and take the same amount of force, but along an opposite direction. Therefore, the two vectors are mutually additive inverse. The sum of them must always be 0. As a result, time derivative of first particle's momentum and second particle's momentum, that is this. Okay, and that is vanishing. And why don't we substitute this one, P1, M1, X1 dot, P2, M2, X2 dot, take the derivative, then masses are constant in non-relativistic Newtonian theory, so derivative appears twice as an acceleration only. And again, this one can be originally expressed as a mass times velocity sum. Time derivative must vanish. Must vanish means something's time derivative is 0. That means conserved quantity. For example, total mechanical energy time derivative is 0. Total mechanical energy is conserved. In here, this derivative is 0. That means this guy without derivative, so this guy is a constant. And what's that? This is P1 plus P2, sum of the linear momenta. That is called a capital P, that is total linear momentum of the two-body system. Total linear momentum of two-body system under no external force except for their own communication through internal force is always conserved, constant, conserved quantity. By the way, this is the nothing but the derivative of this. But this one, we are familiar with this by definition. Numerator of the center of mass is this. So why don't we divide this one by total mass and cancel the division by multiplying outside. And by definition, this is the center of mass. Time derivative of center of mass. So velocity of the center of mass multiplied by the total mass is the total linear momentum that is constant. That is constant. That means center of mass has a constant velocity. For example, center of mass was at the origin, then it will be at the origin forever. Something like that. Therefore, this one is a very, very useful. And the concept of center of mass basically comes from this law of action and reaction. It is a natural consequence of net action and reaction to have a closed system, isolated system, whose total linear momentum is always conserved. And the acceleration of the center of mass is completely determined by the net external forces.